All right, so in the scatter plot, what are the three things? If I asked you just to describe the scatter plot, what would be some of the things you would need to describe? What's the spread? What's the shape?
The spread, you could do the range.
Of what? Which variable?
The minutes, the interval.
Okay, so here's the first thing. When you have two variables, you're not going to act like you have one variable. So shape, center, and spread is out the window for these. Instead, we looked for strength, form, and direction. So I might look at this and say there is a moderately strong, positive, linear relationship between the duration of an eruption and the interval since the last eruption. Because of course, I would include context in my answers, right? All right. Now, this is a very special scatter plot. This particular one is every single eruption. Okay, and which means the line on this scatter plot is the population line. Which we have approximated down here. Now, if I ask you, what is the slope of this line, what would you say? Here's the equation. Using the equation, what's the slope? The 10.36. Okay. Now, so this 10.36 is the population slope. The symbol we use is beta. So that's the Greek letter B for beta. It's kind of a curly Q B. As long as it's anywhere close to a capital B, you'll probably be fine. Okay. And the 33.97, that's my population intercept. This is stupid because it's not the same one, but we call that alpha. But it's different than, say, the alpha of a test. But don't worry. You'll never, ever, ever use... we're never going to care about this one. Like, it's going to be there, but when we're looking and trying to decide, is there a relationship between two variables, or to describe the relationship between two variables, we want to describe how they change together. That's the slope. All right, now, as we look at this, I could take instead of taking every single one of these eruptions, I could have taken a sample of 20 eruptions. And I'm highlighting the greens in mine so that you guys can see them. Okay, so typically what happens when we gather data, we don't look at every single possible thing. Instead, we get a sample. Okay, so for the equation for the line for these 20 points is y hat equals 32.8 plus 10.2x. Okay? Are you noticing that the equation of that line is different than the equation of the line for the population? Is that weird that the sample doesn't match the population? No, because what do we know about samples? They're not perfect, yeah? So now these ones are called an A and a BX. Okay, so this 10.2 is a B. It is the slope of a sample. So what I'm going to start doing is couldn't we make a graph of all of those sample slopes? So let's see. I'm going to go from 7, 8, 9, 10, 11, 12, 13, something like that, okay? And 10.2, there's my first sample slope. Is everybody good? But what if instead I took a different sample? What's the slope of this line? 7.7. So that's this one. And the slope of this one? 9.5. Everybody good? Now, this is the sampling distribution using 3 values for B. What if I took, I don't know, 1,000 samples and found their slope? You guys with me? You guys, what was the population slope? 10.36. We feeling okay with this idea? I want to go back to this initial population graph, okay? And like, let's look at this. Oh, that's a terrible color to use. Let's look at this point right here, okay? Which is essentially like x equals 1.8. If you look at only the points at that line, do they look approximately normal? Where they're mostly towards the center of the line and then they spread out towards the outside. Is everybody good? And so what we would want, keep doing that. What we would want is that same, like, throughout the line. Doing sideways normal curves is not going well for me. Okay, you would want it to be normal all the way through, give or take. Now, are you with me that the mean of this was here? How could we describe the distance of other points near the line and whether or not they're normal? What word do we use to describe how the variability of one of these spots? Oof. That's what this graph looks like, is. So we had the 10.2. We had the 9.5. We had the 7.7. It's probably this one. Are you guys with me? Now, why aren't all of these the same number? Samples are not perfect. So these just represent, I took a whole bunch of different samples, measured the slope. This is all of them. And if I asked you guys to describe what you see in this sampling distribution of the sample slope, which is what we would call this, what do you see? Now we have just one variable, it's just the slopes. Okay, now we would do shape, center, spread. And what would you say about the shape, center, and spread of this graph? It is approximately normal. What about the mean of the different slopes? What do you think that is? 10.3. It looks like about 10.3. We all in agreement with that? Does anybody want to try a more precise guess?
125.
So it's equal to beta, which happened to be 10.36. Now, to do this last part, again, I'm gonna do some reviewing in general so that you guys can get some vibes for some other stuff that's gonna happen. Is there a way we could use the graph to figure out the standard deviation of these B's? Oof. Cool. All right. Let's see how I do here. All right. Does anybody remember any rules with normal distributions? There's a pretty big rule for normal distributions. I'm going to give you a hand signal. You ready?
30.
Oh, 90.
68,
68.
95, 99.7. And that should include all but like the tiniest percentage of our values. And so what I'm going to do is I'm going to go like this. Give or take. Do those look to be equally distant from the mean? And you guys, to get out all the way to the outermost data values, that would be 3 standard deviations on each side. Is everybody with me? So if I asked you to approximate this distance, what would you say it is, give or take? 4? So what do I know about that 4? That is approximately 3 standard deviations. Now, you guys, I will give you all the information you need. You would never in your life have to do this in the Unit 9 context. You could be asked questions, like multiple choice questions, where they give you a histogram and ask you to estimate the standard deviation. It'll be a normal one if they do. This is how you could get there. Is everybody okay?
Master, just so that I can write it down, what are the like ones that go with this again, like the 1 point with the 68, 95, and 97? Is that the thing? Like the 1 point with the z-scores?
The z-scores would be, for 68%, would be -1 and +1, because your z-score is number of standard deviations from the mean.
Okay.
The 95% is 1.96, but essentially 2 standard deviations, and so on and so forth. But you to find those, because we're going to get to it today anyway. The reminder is, you say, if I want to be, say, 95% confident, I do either inverse norm or inverse t, depending on what I'm doing, and I use the values from the tables. The rest of this is just talking about, like, you have the population line and the sample line. We're going to spend all of our energy, we want to use B to conclude about beta. That's no different than using X bar to make conclusions about mu, or P hat to make conclusions about P. Are you guys with me? Like, they're all the same thing. All right. And we're going to talk about 2 different procedures. We're either going to do a T interval for beta or a T test for beta. It depends. How far? And to do any inference procedure for beta, we have the same set of conditions, whether it's an interval or a test, and 3 of them are going to look really, really familiar. For instance, is the random condition a weird condition? Does that sound unfamiliar? We've been doing random condition for it doesn't matter what kind of test, yeah? Independent is not new. Okay? Normal is not new, though the way we're going to check that condition is going to be a little bit different. Okay? So, the first condition we're actually going to check is linear. And here's the deal. You guys, you want to make sure the sample suggests that the population is linear in shape, because otherwise you don't have a consistent slope. What makes something linear is that the slope is the same the entire time. Is everybody good? And so there's 2 different ways you're going to check the linearity of that relationship. One way you could do is say that the graph of the scatter plot shows a linear pattern. The other way you could say that is the residual plot shows no pattern. Now, you guys, when we do this, okay, I will always give you all the graphs you need. But you need to make sure that you're being specific as to which graph you're using. So we will continue to get lots and lots of graphs. And if you just say, if I give you 3 graphs, all different graphs, okay? And you say to me, the graph is approximately normal. I don't know which graph you're talking about. Everybody with me? So this is a place where clear and very specific communication is really important. So you wouldn't just say, oh, the graph shows a linear pattern. You would want it to be, the scatter plot shows a linear pattern, okay? Because depending on which graph, man, if you say the residual plot has a linear pattern, that's a problem, and the line is not a good model, okay? Independent, this one's pretty easy. It's most likely going to be the 10% condition. It could be that dependent responses to treatments are independent, or individual responses to treatments are independent, but it's probably going to be the 10% for this one. Okay. Now, normal. Normal's not about the beta. A point from the line, y'all. Yeah. So what you're going to do is say the graph of the residuals, which is not the same thing as the residual plot, but we'll talk about that in a second, is approximately normal. All right, to talk about what we call this equal variance, I'm going to sketch you a really bad scatter plot for this condition, okay? What's wrong with this scatter plot? Is it positive? Linear? Like, if I sketch in this line, would we see a pattern on the residual plot? We wouldn't. So what's wrong with this scatter plot? What's a key feature of it? If I draw in those like normal curves, that's a bad point to do it from. I'll do it here. I do that for, say, this point. Do you guys see that the standard deviation on this side for this normal curve is a lot bigger than the one for this one? Mm-hmm. Okay, and as you kind of look at the graph, I look at this and I can say like, hey, man, it feels like this side is way more spread out than, say, this side. Everybody good? Okay, and so the variance throughout the graph changes. It's not equal. Equal variance would be, say for instance, like when you look at this one, they're all about the same distance from the line, give or take. So not only are they normal, they're also about the same distance from the line across the whole thing. Now, the easiest way to check for this is that there is no fanning in the residual plot. And then great news. The random condition is exactly the exact same as we've always checked that random condition. All right. So T interval for slope means that my critical value is a T star. Okay, which means we'll use, to find that T star, we're going to use inverse T. I'll make that a lot neater because that looks gross. But in this case, using for inverse T, because remember T graphs have a degrees of freedom, you are going to take your sample size minus 2 instead of your sample size minus 1. A way to think of it is you subtract 1 for each variable. Since scatter plots have variables on the horizontal axis and then a different variable on the vertical axis, you're subtracting 1 for that horizontal axis and then another one for that vertical axis. This is an easier way to kind of think through. Okay? B is going to be the slope of your sample. And the standard error of the B will be given to you. You just have to fill it in. All right. So let's go through an example real quick. This.
Oh, okay, so it's the same. Cool.
That is on your formula sheet. And then they actually have a formula for the standard error of B. You don't want to use it. You're going to mess it up. There's no doubt in my mind you would mess it up, and it would be so many things you have to remember that I don't feel comfortable asking you to do it, even showing you how to do it. Okay?